2.6 combinations of transformations. Before we actually get into an example on this lesson, there's a whole bunch of little guideline type things that we need to be aware of, and essentially it is what it says it is. We're going to put all of those combinations all the transformations we have been learning about together and deal with them all at one time, whereas so far you've dealt with just translations up and down, left and right, or reflections, or stretch and compression, vertical and horizontal. Now we're going to be able to do it all at once. That's what this is here for. But first, we're going to run through some of the basic parent functions here. Okay, so these are, like, this is a type of function. Do you know what type of function this is? That is a linear function. And do you know what the function looks like?
A line.
Straight line, goes through 0, 0, and y always equals x. So where x is 2, y is 2. Where x is 3, y is 3. Where x is negative 2, y is negative 2. Where x is negative 1,000, y is negative 1,000. Okay, straight line. What is this function?
Quadratic.
Quadratic. This is the most basic quadratic. It's called a power function. That means it just has one term, and it's the variable to a power. It's a quadratic function here, and what does that one look like? Parabola that goes through 0, 0, facing up. So anytime you deal with transformations made to a quadratic, it's going to be this shape. It's going to get stretched, compressed, reflected, or moved left, right, up, down. Okay, and these parameters will do that. What is this function?
Oh, it's not a linear, but it goes like kind of on a.
Yeah, what's it called? Yeah, it's the square root function. And basically, it's the inverse of one leg of the quadratic function. So actually, if you took this right side of the quadratic function and you reflected it over the line y equals x, which we get to in our next lesson, it'll look like this.
Bam.
And this one?
That there, sir, is a. Not sure.
Starts with an R?
Rational.
Rational. Rational function. And it looks like this. It's two legs. Goes through 1, 1, and it goes through negative 1, negative 1. And anytime
I don't get how there's two. I never get that.
That's okay. You don't, well, because it's 1 over x, so x can't be 0. So that means this line right here, the function will never cross this line because x can't be 0. It's not part of the domain. And because x can't be 0, I'm not going to explain it right now, but because x, this thing can never equal 0. It's always going to be 1 over something. So y also can never be 0. Y can be infinitely big and infinitely small and infinitely close to 0, but it will never be 0 because 1 over anything can never be 0. So x can't be 0 because it's in the denominator. Y can't be 0 because there's no value of x that would cause this to be 0. Anyway, if we're dealing with any of these functions or any other function in the whole world, we can actually think about it in terms of this. Okay? This describes the transformations that are made to a function. What does that mean? Well, what do we have inside here? We really have, don't write this, but basically what's hidden inside here is y equals f of x. That means the graph is the graph of the function f of x, the value of the function, anyway, when you put in x. So that's hidden in here, y equals f of x. But now here's some things you can do to it. You could do a to it, you could do k to it, you could do d to it, and you could do c to it. We're just going to quickly talk about what each one of those things does.
I know what k does. I still don't get what k does. That's the only thing.
What does a do?
It tells you if it's up or flips up or down.
So don't think, yeah, your brain is probably thinking in terms of quadratics, which is okay because that's pretty basic for us. But again, you can apply these to any function. You could apply them to a cubic, okay? You could apply them to a quartic. That just means that out here you're going to have to the power of 4 or to the power of 3, okay? But this is just describing the transformations that are made. You're most associating it with a quadratic because it kind of looks like vertex form, those kinds of things. And vertex form is a really simple way to read transformations. But again, these things can be applied to any one of these parent functions. So what does a do again, please?
Stretch or compress.
Be more specific.
Vertical.
Vertical. vertical,
Do we write this?
yes please, stretch, compression, reflection. Vertical, stretch, compression, or reflection. What does K do?
Horizontal.
It's being multiplied by x, just like A was being multiplied by the function. Horizontal, stretch, compression, or reflection. What does D do?
Isn't that the y-intercept?
Nope. Give you a hint. It's tucked in here with x. It's going to modify the x by addition or subtraction.
Makes it move horizontal.
Yeah, horizontal, what?
Translation.
Translation. D units.
So just side to side.
And I'm going to actually take that off because you already know that, and I didn't put it for the other two. And what does C do?
Vertical translation.
Vertical translation. All right. So these are the 4 things. There's more than 4 because A and K can do multiple things. But these are the 4 parameters that will transform a given function. Now, sometimes you only have a few of these involved. Sometimes you only have 1 of these involved. Sometimes you have all 4 of them involved. When you have a bunch of them involved, bunch of parameters modifying a parent function, do you think it matters which order you perform the transformations in?
Oh, no.
Let's find out. Okay, at the bottom of page 21, you have an investigation on translations, and it's going to tell us if we can or can't apply things in order or not in order. Is order important? So we're given the function f of x. So you have f of x equals x squared. And we're going to do some things to it. On the left, you can see that we're going to create g of x. And g of x is f of x plus 3. Okay? F of x plus 3. So what does that mean? Well, that means for g of x that I'm going to sub in what f of x is, which is x squared, and I'm just going to add 3. Okay, that's now my new function g of x. What transformation was applied here?
You just subbed in what f is.
Yeah, I subbed in the function f of x is x squared. So where I saw f of x, that means I could just put its function in.
Is f of x always x squared?
No. In this case, it is because we're dealing with a quadratic. And that's the base function of a quadratic. F of x is whatever it tells you that it is. In this case, they're telling us that it's x squared. So what transformation did I apply to x squared?
You squared the x.
No, that's the I'm given x squared and I did something to it.
3.
I moved it up 3.
Yeah.
Okay, so I performed a vertical translation. And now look at h of x. H of x says take g of x, but when you sub in x, you're going to actually sub in x plus 6. Now, what transformation is this?
To the left. No, yeah, to the left 6.
So this one went up 3, and then to the left 6. Okay? Let's find out what we end up with.
Oh, that's both of them. Okay.
So now let's find out wherever I see in g of x, wherever I see an x, I'm going to put x plus 6. So now I have x plus 6 in brackets squared, and I still have plus 3 out here. I'm going to now just simply... Can you tell what I did? We can follow that so far? Okay. All I did was where I saw an x in in g of x, sorry. In order to create h of x, I had to put in x plus 6. So I did that. So now I'm going to just expand this and add 3. So this is x squared plus 12x plus 36. We're good with that?
I
The trinomial. Just one sec, ask it in a second. So I've got x squared plus 12x plus 36, 36, sorry, and I'm going to add 3 to that. So I have x squared plus 12x plus 39. And that is h of x. We were given g of x, f of x, h of x. We were given the transformations that need to be applied. We did a vertical shift 2 up, vertical transformation, and a horizontal transformation 6 to the left. Okay? On the right side of that line, you have a new problem to take care of. You're doing it with, starting with the parent function, f of x equals x squared again. But look at the transformation that we're applying first. What transformation is going to be applied if we sub in x plus 6 wherever we see x?
To the left.
This is going to be to the left, 6. Okay? So let's see what we end up with. mx equals, I'm just taking f of x, but everywhere I see an x, I'm going to sub in x plus 6. And if I simplify this, I get x squared plus 12x plus 36. Then it says r of x is m of x plus 3. Okay? What transformation is being applied here?
Up 3.
Up 3. Can you see the connection here? On the left, we went up 3, then over 6. And here we're going over 6, then up 3. Different order, but watch what happens. mx is this phrase right here. And I'm going to add 3. Gives me x squared plus 12x plus 39. What do you notice?
You just added 3 to your vertical.
Can you look at this and this?
They're the same function.
They're the same. Did it matter which transformation I did first when they were both simple translations? Did it matter if we did vertical translation before the horizontal translation?
Yes.
No.
No, it didn't matter. We got the exact same function. We did it in different orders and we got the exact same function. Okay? So when you're just dealing with moving it, it does not matter if you move it up first or left first or down first or right first, as long as you're doing them right, obviously. Based on the last one, I have a question for you. This time we're going to apply stretches, horizontal stretch and a vertical stretch, to the same function. Do you think it matters what order we will do it in?
Yes.
Okay, we have f of x is x squared. First, we're going to create b of x. B of x is 5 times f of x. What's the transformation being applied there?
X squared.
Younger.
So the original function is x squared. So
Uh,
b of x
5x?
is going to be 5 times x squared. What is the transformation that was applied?
Vertical
A vertical
translation.
stretch by a
Factor of
5.
factor of 5. Thank you. Good enough. Okay, we're also told
Hello?
the transformation for p of x. P of x, we're going to take b of x, but wherever we see an x, we're going to put in 1/4 x. What transformation is that?
Well,
That is a horizontal stretch by a factor of 1/4.
Close.
Factor of
negative
4.
1/4.
by a factor of negative 4.
Yes.
Why
Factor of 4.
By a factor of 4. It's okay if you're still foggy on that. It means you didn't do your practice problems from yesterday,
That is
and you have lots to catch up on. Okay, so everywhere I see an x in b of x, I'm going to sub in 1/4. It's not right. 1/4 x, and it's still squared.
How do you know whether to call it B of X or P of X? You just choose
I
one.
will tell you.
It literally told us, and I just was copying what it's telling us.
Oh.
Okay, so now what happens here? 1/4 and x need to get squared. Do you know what 1/4 squared is?
1/16.
Thank you.
Good job.
X squared. So we're looking at 5/16 x squared. Okay, this is our new function p of x after applying a vertical stretch, then a horizontal stretch.
There's no brackets between 5/16 and x squared.
No, because the default operation in algebra is multiplication.
Sorry, dude. Yeah. Did great,
I
deal.
was just wondering.
Okay, same thing on the right hand side. We're going to start with f of x equals x squared, but this time we're going to go for n of x, and it is defined as being f of x, but
To the left, to the left.
it has a what kind of transformation?
I'm gonna say
Horizontal
stretch by a factor of 4.
Thank you.
Which we have a quick question of the other one that you did.
Horizontal stretch by a factor of 4. So
Yeah, see that.
n of x tells me that I'm going to take f of x, but wherever I see an x, I'm going to put 1/4 x instead. Okay? So n of x is 1/4 x squared, which is 1/16 x squared. The next transformation is defined as s of x equals 5 times n of x. What transformation is this?
Vertical stretch by a factor of 5.
Vertical stretch by a factor of 5. Can you see how we're doing the exact same thing as the left side, just in a different order again? So I got 5 times n of x. N of x is right here. It's 1/16 x squared. Multiplication is commutative, so this is just 5/16 x squared. Did it matter which order we applied the transformations in? It did not. In the next one, we are going to apply a stretch and a translation. Do you think it is going to matter what order we do it in?
No.
Yes. This time I'm going with yes.
Okay, we're given f of x. We'll start with f of x again, which is x squared again. Okay, we've got j of x. J of x equals 2 times f of x. Okay, so all we do is we get j of x. By the way, what kind of transformation is this?
Vertical translation.
Vertical
Stretch.
stretch by a factor of 2. So we have 2x squared. This is a vertical stretch by a factor of 2.
Well, we always have to say vertical stretch by.
All right, the next transformation that's happening here is s of x, and it says to take j of x and add 5. What type of transformation is that?
Horizontal.
Careful.
Horizontal.
Vertical
Vertical?
stretch.
No.
Vertical translation.
Yeah.
It's just moving. You're just adding
Oh,
5.
it's a different one.
You're just adding 5 to the value of every single point.
Yeah,
You're
that
not
makes
multiplying it by anything. You're just moving it up. Vertical translation up 5 units. Okay, so we take j of x, which is 2x squared, and we add 5.
I figured it out.
About time. Kitty.
That's done. That's simplified. That's our transformed function.
Ben.
Okay, so on the right-hand side, we're going to do the same thing, but in a different order. And
So
some of
you
you
just
think it's going to
add-
matter, and some of you think it's not going to matter.
So you just add
I just want a different way.
you just add the equation sx to your equation jx.
It says s of x. Sorry, that should say s of x.
Oh,
It says s of x is j of x plus 5. And you know what j of x is, so you just do j of x plus 5.
You sub it in.
Okay.
Yes,
Now we're going to do them in opposite order.
Until you do practice.
This time we're going to take f of x, and first we're going to move it up. Okay, so we're going to do our vertical translation up 5. Then we're going to do, down here, you'll see we're going to do our vertical stretch by a factor of 2. And you think it's going to matter?
I think it's gonna matter because.
Okay, here we go. F of x is x squared, so we have x squared plus 5. That's q of x. And the next one, t of x. T of x says to perform a vertical stretch by a factor of 2. So we're going to take 2 times q of x. Please pay attention to what this looks like. 2 times q of x. I need to make sure that's 2 times the whole group, q of x. Now to simplify, I distribute the 2 to both terms. I end up with a function t of x that is 2x squared, oh, that looks good so far, plus 10.
Yeah! We got it! Boom, baby!
Did it matter?
Yes.
Yes. Okay, so now I'm just going to tell you the right order to do it in, because you must always do it in the right order.
Is that always for everything that we've been doing, or just this certain?
Transformations. Again, you've only ever done one type of transformation at a time. Now you're going to be doing multiple transformations at the same time. So please find a spot to take this note, either at the bottom of that page or the top of the next page, wherever. Or looks like there's actually a spot at the end of the lesson, page 24. Page 24, after example 2, you can take this down. When combining transformations,
Why are we writing this?
Bottom of page 24.
24.
when combining transformations, comma, capital letters, order matters. Yeah? Apply parameters A and K before D and C. If you want to help yourself out with some bedmass thinking, these ones deal with multiplication, right? They are factors. Factors. You stretch by a factor, you compress by a factor, okay? You reflect something by a factor of -1. So they deal with multiplication.
Addition.
D and C, what do they deal with?
Addition.
Or,
Subtraction.
so just like in bedmass, when you do multiplication, division before addition, subtraction, same thing when you're dealing with transformation. So now on a test, when I say identify in the correct order the transformations to the function blah blah blah, you will know that you're looking for your vertical stretch compression reflection and your horizontal stretch compression reflection, which, by the way, doesn't matter which order you do those in.
No.
No. Before your vertical and horizontal up and downs, left and rights, translations. Does it matter which order I do these in?
No.
No?
No. Does not matter. As long as I do my stretch, compression, reflection first, then this is just moving it around. Makes no difference if I move my hand to the right and then up, or if I move it up and then to the right. Okay?
So it's only when you're doing both that it matters?
Only when you're doing both that it matters. Example 1, combinations of transformations. So the first one is pretty straightforward. We're always, I'll just write down what they give us. We're dealing with the parent function f of x equals x squared. And we're told that g of x is going to be 1/2 f, big bracket, 4 x minus 3, close bracket, minus 2. Okay, please pay attention. This is function transformation. This g of x, this is not the equation for g of x. Okay, please be very listening. This is not the equation for g of x. This describes the transformations to f of x that will create the new function g of x. Okay? This is describing the translations. How do I know that? Because f of x is still in here. This says take the function f of x and do this stuff to it.
Wouldn't you just be able to sub that
Now,
stuff into the graph?
all the time, we're going to be comparing to this statement. Y equals a. Okay, I'll put an F there just because that we're talking about the same thing. K x minus d, close bracket, plus c. Okay, so you know what these things do. So now let's go ahead and identify the parameters that are here. Okay, let's identify the parameters that are here. I'm going to do it 2 different ways. First, I'm just going to do it by pointing and you telling me what they're going to do. What's this?
Horizontal, vertical,
Vertical, stretch,
or compression.
Stretch or compression, which one is it?
Stretch.
It's in between 0 and 1. So it's a compression, and we're just going to use the factor that's there. Vertical compression by a factor of 1/2. Okay. What is this?
That's horizontal stretch.
Stretch. Compression.
Why are we? What?
Horizontal compression. What are you talking? Oh,
Okay. The horizontal one is by a factor of 1/k. So whatever 1/k is will determine if it's a stretch or compression.
why would
K is 4, so the compression is 1/4.
I don't understand that.
That's okay. It's because you didn't do your practice problems. Now what? We have two more possible transformations here. What do they do? What does this one do?
It's.
Horizontal translation 3 units left.
Please,
Or is it right?
That's right.
Horizontal translation 3 to the right. Because look over here. X minus D. X minus 3. D is 3. Positive. Moves it to the right.
Are we writing this under our graph?
Yeah.
Oh,
You should definitely be writing this.
my bad, dude.
All right. Last one. What does the last one do?
Down 2.
Can you be more specific?
Vertical translation by 2 units.
Vertical translation down 2 units. Okay, that's one way to quickly think about it. For the sake of the example, we're also going to make a list. We're going to make a list of the parameters. So we have A, K, D, C. A equals 1/2. K equals 4. D equals 3, positive 3. C equals negative 2. Sometimes it's helpful just to look at it like this, right in its function transformation notation here. Sometimes it's helpful to write this list, which you'll probably do more often actually. Probably write this list, A equals 1/2, and then you'll say, okay, what does that do? Well, that is a vertical compression by a factor of 1/2. K is 4. What does that do? Oh, that's a horizontal compression by a factor of 1/4. D is 3. Okay, that is a horizontal translation 3 to the right. C is negative 2. That is a vertical translation down 2 units. Okay, that's how you mostly write it. It's nice and organized. And what that allows you to do is draw the graph. Does it matter which order we apply our transformations in?
Yes.
Yes, it does, very much so.
You're already allowed to draw the graph.
We can draw a graph from this, yep, if we apply our transformations in the right order. Now, what was our parent function?
And f(x) equals x squared.
F of x equals x squared, and you have a graph drawn for you there.
Sir.
X squared, make sure, is x squared drawn on yours already?
Yes.
That's nice.
I know, so confusing.
Okay, does it look kind of like that?
Yeah.
Yeah.
Okay, so let's apply our vertical compression by a factor of 1/2 first. So what does that mean? That means every point along here, okay, is going to get pulled back down
By half.
toward the x-axis.
It's hard to judge, eh?
It's going to look something like this. Okay? For you, it's a little bit easier because you have your line, your grid's actually drawn. So basically what you're saying is if it's a vertical compression by a factor of 1/2, instead of going through 1, 1, it goes through 1/2. Instead of going through 2, 4, it goes through 2, 2. Instead of going through 3, 9, it goes through 3, 4.5. Instead of going through 4, 16, it goes through 4, 8. Does that make sense? You're just cutting the y-coordinate in half. Yeah?
Can you also do
You can
half of the little box?
Yeah, yes. If you're on this side and you're at negative 4, positive 16, you're going to be at negative 4, positive 8 instead. Okay? So that's kind of what it should, your new one should look like. Yes? Now, from that blue one, by the way, you're going to probably want multiple colors as you're doing this, and you're going to want to probably draw pretty lightly. Okay, now we're going to try to apply our horizontal compression by a factor of 1/4. and a horizontal compression. That means this blue curve now that we're dealing with, I'm going to actually maybe just get my black curve right out of the way because I have that ability. It's being compressed horizontally. Paying attention? Compressed by a factor of 4. What does that mean? That means every single infinite point along the curve is going to get pulled toward the y-axis by a factor of 1/4. So the distance between our new point and the y-axis is going to be 1/4 the distance between our old point and the y-axis. So I'm just kind of eyeballing it, but you should be able to figure out where it's going through. For instance, if you went through 4, 8, now that is going to be going through 1, 8. So x coordinates are getting cut by 4. Okay? So instead of going through 1, 1/2, which your newest graph does, you're going to go through 1/4, 1/2. The x coordinate gets divided by 4. It's going to result in a pretty skinny parabola. Something like that.
Smaller than x squared.
Yes, half the size actually.
Ooh.
So my black one, if it was still here, it would be somewhere in here. Okay. So now what have we done? Okay, ready? Paying attention? Black, we started with x squared. My blue graph was our vertical compression by a factor of 1/2. That was this. 1/2 times x squared. That was blue. Red, I took a k value of 4. So red one is actually 1/2 times 4x squared. Okay, which equals 16x squared divided by 4 is 4x squared. So this is what the red one actually looks like. The graph of the red parabola that you have so far is 4x squared. Okay? No, I lied to you.
Wow.
Yeah, I was about to say.
I lied to you because this is not in brackets.
Yeah.
This should be in the bracket with it, like that. So it's not actually 4x squared.
It's 4. No.
Are you sure?
It's
Before I
8.
do it.
Oh, because this is a 1/2. That's why.
Yeah.
Okay, there we go. Sorry about that. So this is when we did the horizontal compression by a factor of 4. This is now the function that we have. Okay, it looks like this, and it's 2x squared if we simplify it, because it's multiplication 1/2 times 4 times x squared is just 2x squared. Okay, so the red function that you have drawn is actually the same as 2x squared. Now what are we going to do? Well, now we're going to apply our transformations. We're going to move it left and right, up and down. Does it matter which way we do it?
No.
I'm going to get 2 more colors out. Okay, and if I were doing this for homework, I would certainly do these both at the same time. Essentially what we're going to do is we're going to take this 1/2.
I need a blue.
Get all
These
this
are
red.
funny.
No, I need my red.
Ah.
We're going to take this 1/2 4x squared,
I'm confused.
but everywhere we see an x, we're going to put in x minus 3. And we're going to subtract 2 from it. Okay, that we're applying both of these transformations at the same time. Horizontal to the 3 to the right and vertical down 2. So I'm taking my vertex of this red one, and I'm just going to move it to the right, 1, 2, 3. I'm going to move it down 2.
It's way down there.
And I need to keep it the exact same shape, tall and skinny, because it still has the same shape as 2x squared. And it'll look something like that. Yours will be better than mine, I'm sure,
Oh,
because you have some graphing lines there.
I wouldn't go that far.
Okay, so that was a bit tedious. That's our first time through it. But basically what we did is we performed A and K, and then we performed D and C. Slight typo here. I need my exponent to be outside of the brackets because the parameters K and D get applied to X before it gets squared. Okay? So this is our newest function. This is actually the function g of x. Okay? This is the function, and this is what it looks like. If we had to convert this into standard form, you could do that by just using BEDMAS and working through it step by step, and you would get it into standard form. It actually does want us to do that. So I'm going to do that really quickly. Okay, BEDMAS basically just means do things in order. Brackets first. This bracket is already simplified, but this bracket is not, so I can expand that by multiplying 4 by x and 4 by -3. That gives me 4x minus 12. Then I have to take care of my exponent. Okay, which is going to give me 1/2 out front. If I FOIL this in my head, I get 4x squared, which is 16x squared. 4 squared times x squared, 16x squared. I'm going to have -48x's and -48x's. That's going to be 96x's, -96x's. And then I'm going to have 12 squared, which is plus 144. Now I distribute the 1/2 to each of these terms. That gives me 8x squared minus 48x plus 72. And at the same time, I'm also going to subtract 2 from that. So I have actually plus 70 is my last term. Okay, this would be standard form of g of x. But this equation right here is the exact same as this equation right here.
That's
Just in
correct.
standard form.
Just in
And
standard
that
form.
What there was in vertex form, or
Yeah, you could say that was in vertex form, but it's...
what form
Yeah.
would that be in?
Yeah, I guess it is in vertex form. It's different now because we can we have a horizontal stretch of compression that we never had before. We're looking at example 1. We've already completed it. You performed the transformations. We drew the graph. I'm going to teach you a different way to do it that you might find a little bit easier, okay?
On the same graph.
You're going to have the space under the graph. It's a table of values.
What?
Just let me draw the table of values first, and then I will pause and you can draw it, okay?
I think I've room
So
for
you-
that.
Thanks. Look at it after I'm done drawing it. Determine how much space you need and where to put it, and then we can have this conversation. Thanks very much. Okay, now, here's what it looks like. It's like a regular table of values. Again, don't draw yet, just watch.
Don't draw.
With an x and a y, right? This is an input and an output. Our parent function here is f of x equals x squared, okay? So what I'm going to do first is I'm just going to pick a whole bunch of coordinates that fall on the line, points that fall on the curve x squared, okay? So watch. -2, -1, 0, 1, -2.
Can you basically choose any numbers?
The y coordinates that go with those x coordinates then are -2 squared, which is 4, -1 squared, which is 1, 0, 1, 4. Okay? My points are arbitrary. I know that the parent function centers around, there's a lot of action here. So those points are helpful to choose.
Here you go.
Okay? Now, what this is called is an extended table of values. What does that mean? Well, it means I'm going to extend it because we know there are transformations that can be applied vertically. They are stretches or compressions, reflections, translations. Okay? SRT. Now, I can make the same adjustments to my x coordinate, horizontal transformations. I can do a stretch or compression, a reflection, and translation. All of these things are determined by the new function g of x. Okay? So this notation, this transformation function notation, tells me what I'm doing to f of x. Well, here's f of x right there. Okay, this is all the data I need for f of x. It's the basic core of what f of x looks like. Right, there it is. Now I'm going to start doing stuff to it. Notice the order that I put them in. I'm going to work my way out and out. So I'm going to first perform my vertical stretch compression, then my vertical reflection, then any vertical translations. That's going to give me my new y coordinate. Then I'm going to look at my x coordinate, my x values. I'm going to perform any stretch compressions, any reflections, then any transformations. That's going to give me my new x coordinate. And this x coordinate over here is going to be the ordered pair with this y coordinate over here. Okay? So we're basically just saying these are the points, the key points of the parent function, and these are the new points on my transformed graph. It'll make sense as we do it. Go ahead and copy that graph down. Another thing that might be helpful before we start actually writing in our new values in our chart is to identify the parameters of the transformed function. So we have a, k, d, c. A is 1/2.
We already wrote
So that's a vertical compression by a factor of 1/2. K is 4. Okay, so that's a horizontal compression by a factor of 1/4. D is 3, positive 3. So that is a shift to the right 3 units. 3 right. I'm just shorthanding it quick. Yeah, you already have these. That's great. Vertical compression by a factor of 1/2. C is -2, so we're going down 2. Down 2. Now, which of these affect the y's and which of these affect the x's? Well, if we're doing a vertical stretch or compression, vertical, we're dealing with y values. Okay, so this guy deals with y values. If we're doing a horizontal stretch compression, well, that's going to affect the x values. D is a movement 3 to the right. Right and left, horizontal translation. So that's going to be our x values. And down 2, that's going to be our y values. All right, let's start applying these things. Now I've dissected this equation. I don't even really need to go back and refer to this equation anymore. I'm just going to work from the inside out, making sure I'm doing my multiplication division ones before my addition subtraction ones. Okay, SRT is the order, and backwards here SRT from the inside out. Here we go. Y values. Stretch or compression. We have a vertical compression by a factor of 1/2. All I need to do is take my y coordinate and multiply it by a half. 1 divided by 2 is 1/2. 0 divided by 2 is 0. 1 divided by 2 is 1/2. 4 divided by 2 is 2. Okay? Now we have applied just this transformation. So that means if none of these other things were here, if it was just g of x equals 1/2 x squared, we'd be done. X, y, x, y, x, y, x, y, x, y, plot your points, graph it. Done. Okay? But there's more here. Is there a vertical reflection? Is there a negative sign out here? No. So I'm just going to wipe out that column.
Sir.
Okay, no change. That means this is still my y coordinate. Is there a vertical translation?
Yes, sir.
Yeah, down 2. So no matter what y coordinate I have, I'm going to subtract 2 from it to move it down. So my new y coordinate here is 0. This is half minus 2. That's going to be negative 1.5. 0 minus 2 is negative 2. Half minus 2 is negative 1.5. 2 minus 2 is 0. Okay, so you can see all we did was take this parabola and we moved everything about it down 2. These are our key points, but this is actually happening to every infinite point on the curve. It's all getting moved down 2. You can see we still have a lowest point, okay, a lowest value here, but now it's at negative 2, which is the y coordinate of the vertex. That's convenient. Good. We're done. SRT on the vertical scale. Y values are done. X values. What's happening to our x's? Well, we have a horizontal compression by a factor of 4. Sorry, 1/4. Okay, so we're going to take this value, negative 2, and we're going to divide it by 4. Or multiply it by 1/4. However you want to do that, you end up with negative 2 over 4. which is negative 1/2. Okay, negative 1 divided by 4, that's negative 1/4. 0 divided by 4, 0. 1 divided by 4, that's 1/4. 2 divided by 4, that's 1/2.
Bless you.
Is there a horizontal reflection? Is there a negative? Is K negative or is K positive?
Positive.
It's positive, so there's no reflection. Okay, so we're going to cross that out. Don't need to do it. Is there a horizontal translation?
Yes, sir.
Yes. 3 to the right. D is positive 3. So that means all of my x's, I'm going to add 3. Don't be tricked. You're not subtracting 3. You're adding 3. Okay. Negative 2 plus 3 is 1. Sorry, I'm not at negative 2 anymore. We're at negative 1/2.
Ooh,
Okay, don't go back to there. We're at negative 1/2. We're going to add 3. That's going to be positive 2.5. Negative 1 plus 3 is positive 2. 0 plus 3 is 3. 1 plus 3 is 4. 2 plus 3 is 5. Okay? So you're right. Emily caught the second mistake. We're at 1/4. 1/4 plus 3 is 3.25. And 1/2 plus 3 is 3.5.
Would that be the same for the second one?
No, because it was 0 and 0 is the same answer,
No,
thankfully.
second one.
Yeah.
Quarter.
Yep, you're right. That should be 2.75. I'm still only counting that as one mistake altogether there.
Well, we'll give you it.
Yeah. You're feeling pretty optimistic about today. You have 1 hour left to catch a third mistake.
Okay.
So what did we just do? We created new image points. We created the set 2.50. That's on the curve.
Mhm. No.
2.75, negative 1.5 is on the curve.
Oh, I see what we did.
3, negative 2 is on the curve. 3.25, negative 1.5 is on the curve. And 3.50 is on the curve. Go ahead and check your drawing to see if those points are actually on the curve.
That comes a new line.
So our drawings aren't perfect, but your new drawing should go through all of these points. Okay? So this is a second way to draw that new graph. You can do it by applying the transformations one by one and changing your graph as you go, or you can do this extended table of values, get your new points, and draw the parabola through there. Okay, here's example 1b. We're told the parent function is a root function. Okay, you know what that looks like now because we did it at the beginning of the lesson. And this describes the transformations being made to that function. Okay, so we're taking f of x and we're doing all this stuff to it. But take a close look at this. It doesn't look how it normally looks. There's something missing from it.
The
Do we have to make the perfect square triangle or something?
Nope.
Where's the other brackets?
Ah, where's the other brackets? Thanks. Straight in. Good job.
That's the new bracket.
No, I actually just looked at
So
the
what's
brackets.
missing here is k. Okay, it kind of looks like k is 3, and it kind of looks like d is negative 15. But actually our first step is going to be converting it into transformed form, into this proper form, okay? So what we actually need to do is first rewrite g of x, okay? So I'm going to take g of x
Okay.
right here, and what I need to do is actually factor out this 3 from the bracket here. So the negative 2 stays, f stays, and now I'm going to factor out the 3 from the bracket, leaving me with x plus 5. And now you can see all 4 parameters, okay? So we rewrite. Now we're going to list parameters, which means A, K, D, and C. You go ahead and jot down what you think the values of those parameters are. And double check the board when you're done. Now what effect do each of those parameters have on the graph? Okay, we're going to write it properly in the right order. So this a of -2, what is that going to do?
It's gonna go down, so it's gonna be upside down.
Okay, so it's first it's a vertical stretch by a factor of 2, and then it is a reflection in the x-axis. Okay, it's going to flip upside down over the x-axis.
It's
So A is doing-
-15, not 5.
No,
No,
no.
we
Pretty
rewrote
sure.
it. Yeah.
Rewrote it.
Where do you get that?
Factored out the 3, 3 to, out of both terms. Okay, factoring.
You thought you
K, K is 3, so what does that cause? It's a horizontal compression by a factor of 1/3. D is -5, what is that?
It goes to the left.
Good, horizontal translation, 5 units left. C is 4, that is a
Vertical translation up.
4 units up, vertical translation. All right. Now we're going to do this 2 ways again. First we're going to draw the graph just using this stuff, and then we're going to do our extended table of values.
We don't have.
Okay?
What are you talking about?
Should have loads of room.
Is what we're
Anyway,
doing.
that's okay. Here we go. I'm going to draw. The parent function is a square root function. So it goes through 1, 1. It goes through 4, 2.
Look. Yeah. That was a messy page.
Goes through 3, 9. 9, 3, sorry. All right, what are we going to do to this thing? We have to do it in the right order. So first step, let's take, I'm going to do it in green, even though you can't see green. I'm going to do a vertical stretch by a factor of 2, and I'm going to flip this thing upside down. Okay? You ready? Vertical stretch by a factor of 2, and flip it upside down. So here's a vertical stretch by a factor of 2. Basically means every point along the curve is going to be twice as far from the x-axis as the original. So instead of going through 1, 1, it's going to go through 1, 2. Instead of going through 4, 2, it's going to go through 4, 4. Instead of going through 9, 3, it's going to go through 9, 6. Okay? And then I'm going to flip it. So all of the y coordinates become negative. All of the y coordinates become negative. It should look something like that. Yours is, of course, better because you have the grid lines helping you out. All right, we've taken care of A. I did a vertical stretch by a factor of 2 and reflect it in the y-axis. Now, K. K is 3, so we have a horizontal compression by a factor of 3. That means every single point along my new curve that I'm working with is going to be 1/3 the distance from the y-axis. So it's getting pulled in. So if I had a point here, it's now going to be here. Okay?
Wait,
So it's getting pulled in.
I don't get that.
How do you know it's?
So my new curve is going to look something like that.
Because it's 1/3, but it's actually just 3.
So it's going.
Look. By a factor of 1/3.
So how do you calculate?
And now,
I
the
don't know how
last
to graph
thing,
this nicely.
so I'm still starting at 0, 0. I'm flipped upside down. It's changed its shape quite a bit from this black curve now to the blue curve. And the last thing we're going to do is perform the vertical translation and horizontal translation. I'm going to do them both at the same time, okay?
No.
So we did this guy, and now we're going to go 5 units left, 4 units up. So I'm going to take my start point, I'm going to move it 5 units left and 4 units up. Somewhere over here. This point should be -5, +4. And I want to keep the exact same shape as this blue curve, okay? I want to keep the same shape as this blue curve. It's going to come down.
Our graph isn't big enough.
I don't know.
and look something like this.
It's definitely not big enough.
Yes, it is.
What did I do?
I'm doing 11.
When you do a function this way, when you apply the transformations this way, it might not end up being perfect, okay, but you have a pretty good idea of what this thing looks
Not
like.
really.
But before we move on, I want to also do the extended table of values again, okay? So on the extended table of values, you start with x, y, and our parent function is y equals the square root of x. Now, when I'm doing y equals the square root of x, I'm not going to choose my x coordinates, -2, -1, 0, 1, 2. Instead, I'm going to pick points that I know are whole numbers and I know are on this graph. It's the square root function. So I know that it goes through 0, 0. I know that it goes through 1, 1. But then it goes through 4, 2, because the square root of 4 is 2. It goes through 9, 3. It goes through 16, 4. Okay, that's enough points to think about. And now I need to extend my table of values, right? It's called an extended table of values. So I have S, C, it's my stretch compression, R for reflection, T for translation, and then same working out on the X side, S, R, T. You do not need to write S/C. That's kind of understood. Okay, if you need that, then go for it. But it's easy to remember. It's the SRT extended graph, extended table. That makes it a bit easier to remember. So now again, we're going to do things one by one in order to create what? In order to create g of x, which isn't on the screen, so I'll quick write it again. But we're looking at g of x equals -2 times 3 x plus 5 plus 4. All right, vertical stretch compression. This comes from A, and this one comes from A. This one comes from C over here. This comes from K, this comes from K, and this comes from D. If you want the parameters that they come from, that might be helpful to you as well. Your choice on how much of this you write down. Okay, let's look at our vertical stretch compression. Well, the first one's real easy. If I stretch or compress something from 0, it's 0. Anything times 0 is 0. So that's easy. And reflection, there is no reflection. So these are going to continue across one more block. That's probably a better way of doing it than me crossing out the blocks, is just bring that number over if nothing happens. Okay, vertical stretch. A is -2. So we have a stretch and we have a reflection. So we have 1 times 2, that's 2. 2 times 2, 4. 3 times 2, 6. 4 times 2, 8. There is a negative sign, so there's a reflection in the x-axis. My 2 becomes -2. 4 becomes -4. 6 becomes -6. 8 becomes -8.
Wait.
Vertical transformation, we're going to go up 4. So any coordinate that I have here after performing my vertical reflection, I'm going to add 4 to it. 0 plus 4 is 4. -2 plus 4 is +2. -4 plus 4 is 0. -6 plus 4 is -2. -8 plus 4 is -4. Now looking over here at my x-coordinate, starting with 0, 1, 4, 9, 16. What are we doing to it? Well, we have a horizontal compression by a factor of 3. Okay? Factor of 1/3. So I'm going to divide all of these by 3. They're getting closer to the y-axis. 0 divided by 3 is 0. 1 divided by 3 is 1/3. 4/3. 9 over 3 is 3. 16/3. There is no reflection, horizontal reflection, no reflection in the y-axis, so I'm actually going to bring those values over. They stay the same. There is a horizontal translation. We said we're moving 5 units to the left, so I'm going to subtract 5 from all of these x-coordinates. 0 minus 5 is -5. And then it gets a bit sticky. You wouldn't use your calculator. You would still just do it in your head. But, I mean, you could use your calculator too. You could go 1 divided by 3 and then -5. And I'm going to write my answers as decimals, actually. It's easier for you maybe to wrap your head around it as a coordinate if you're plotting points. Okay, then you have 4/3 minus 5. That's going to be negative 3.67, 3 2/3, negative 3 2/3. 3 minus 5 is negative 2. 16 over 3 minus 5, well, 5 is 15/3, so you're left with 1/3 here, which, since we're using decimals, we may as well be consistent, 0.33. So now the new coordinates that your curve should go through, look at this, we have one of them written already, so we know we got that right, negative 5, 4. Then we're going through negative 4.6 and negative 2. That's somewhere around here. Negative 4 point, I'm just going to round to 7, and positive 2. Then we have negative 3 point, right here is negative 3.70. Then what else do we have? We have negative 2, 2. That's going to be somewhere in this range. Negative 2, negative 2. And then we have positive 1/3, negative 4. That's right here. 1/3, negative 4. Okay? So that's the other way to graph it. If you don't want to do it with this, changing the graph each time, you should be able to do it both ways. But if this is easier for you, then go ahead and don't even draw this graph. Just draw the parent function. Then complete this table of values. But you're going to have to know how to set up your first two columns, depending on the parent function. Okay? Take whole number key points that give you enough information to actually draw something.
So the key points would be like what the parent function goes through.
Correct, what the parent function goes through. Then once you get your new points, you can simply plot those points and then draw the curve through those points.
Well, we have to know both ways for the test.
That's a good question. Example 3 is a somewhat real-world situation. It's a drag race, 2 cars. One is faster than the other one. So we're essentially determining for the slower car, how big of a head start does he need? Okay, how big of a head start does he need in order to beat the faster car? So during a race in a sportsman category of a drag racing, it's common for cars with different performance potentials to race against each other while using a handicap system. For example, Byron is racing against Eve. Since Eve has a faster car when they race, it appears as though Byron gets a head start. The distance, E, in meters that Eve's car travels is given by E with respect to T. That's the distance that she travels with respect to time, where time is measured in seconds, 10t squared. Okay, so in the first second, she travels 10 meters. After 2 seconds, she's traveled 40 meters. Okay, she's accelerating, right? It's a drag race. After 3 seconds, she's traveled 90 meters. Make sense? Good. B, Byron's car. Byron, with respect to time, his distance with respect to time is given by 5t plus h squared. Now, this represents his head start. Okay? So when we put a time into his function, you're going to actually add a second because he's starting a second earlier than Eve. Or if his head start is 2 seconds earlier, then you would take the amount of time after Eve starts. So after Eve has been driving for 2 seconds, if h is 2, that means Byron has been driving actually for 4 seconds. Okay? Does that make sense? So that's going to even up the race a bit.
Even
So let's talk about this. Where t is the time after Eve starts. So t is the time not from the beginning of the race necessarily, it's the time from when Eve starts. That's why this t and this t are the same. Okay, does that make sense? And Byron is going to start earlier, that's why this parameter is here. All right, on the same set of axes, graph the distance versus time for both drivers with h values of 1 second, 2 seconds, 3 seconds, and 4 seconds. Okay, so we have Eve, and then we have she is always E equals 10t squared. And then we're going to have Byron with a head start. Okay, so we're going to graph Byron, and you have a little chart there with a 1 second, 2 second, 3 second, 4 second head start. So what happens to his equation then that represents his driving?
You just add the amount of
We
seconds.
just put that in there, okay? So we've got t versus, so Byron here is going to be b with respect to t is 5 times t plus 1 squared. That's with a 1 second head start. We've got 5, then t plus 2 is a 2 second head start. 5 in brackets t plus 3 squared. That's a 3 second head start. And t plus 4, it's a 4 second head start. Eve is always the same right there, okay? Now, we're asked to graph it. Mostly I'm going to show you what they look like, and you're going to do your best to copy it. But this is an exponential graph. So the first one I'm going to draw is Eve. And Eve is 10t squared. So she starts at 0, 0. She goes through, and by the way, do you have, no, you don't. Okay, so hold on. These numbers, your grid lines on the vertical axis are going to be 100, 200, 300, 400, and that's the finish line. 400 is the finish line. And along here, you're going to have, yeah, you can, if you can get it straight across. Every block is going to be 1 second. Yeah? So here's a quick way to do Eve's driving. She starts at 0, 0, obviously. 0 time, 0 distance. At 1 second, she's driven 10 meters, which is not very far. At 2 seconds, she's driven 40 meters. At 3 seconds, she's driven 90 meters. At 4 seconds, she's driven 160 meters. At 5 seconds, she's at 5 squared, that's 250 meters. At 6, she's at 360 meters. And then she's pretty much done the race just after 6 seconds. So that's what her car looks like, okay?
Can you say that one more time?
Yeah, so based on this equation, t seconds after Eve starts her race, so 1 second at the 1 second marker, she's driven 1 squared, which is 1 times 10 meters. 10 meters. After 2 seconds, she's driven 2 squared, which is 4 times 10 is 40 meters. So 240 is on your graph. After 3 seconds, she's 3 squared, which is 9 times 10 is 90 meters. So that's on your graph. Then 4 squared times 10, then 5 squared times 10, then 6 squared times 10. Now, we're asked to draw Byron's graphs, okay? So I'm going to try to do it in a bunch of different colors here. I'm not going to just try to do it in a bunch of different colors. I'm actually going to do it in a bunch of different colors. You don't necessarily need different colors. It's just easier for me to keep track of it here. So I'm going to do the first one in blue. Or, no, purple. I'm going to do the first one in purple. Okay, this one's going to be purple. So his graph is 5 times t plus 1 squared. So at 0 seconds, when Eve has traveled 0 seconds, he has actually traveled already. Okay, so when t is 0, and maybe we need to go backwards for him, this time he'd be at 0 distance at a negative 1 second. That's when he hasn't traveled at all. Okay, now at 0 seconds, he's got 0 plus 1, which is 1. 1 squared is 1 times 5. So he's at 1, 5, which is pretty much nothing. He's at 2. I'm just going to skip a few, okay? I'm not going to do all these points. We're just going to get the shape of it, and then I'm going to use the shape to copy the other ones, because the shape doesn't change. It just is going to move left to right, right? The only thing happening here is a horizontal translation left or right. Left, okay? So I'm going to skip ahead to 3. At 3 seconds, he's 4 inside the bracket. 4 squared is 16. 16 times 5 is 80. So he's at 380. Which is about there. 5 seconds. 5, he'd be at 6. That's 6 squared is 36. 36 times 5 is 180. So he's at 6, 180. And maybe I'll do one at 8 seconds. 8 seconds, he'd be at 9 inside the bracket. 9 squared is 81. 81 times 5 is 400 something. It's pretty much right around
8,400 or 9,400?
Yeah,
8,400.
and you did this, you said the one was 5, but you did it under 6.
Yep, that's okay. So now you can see if Byron starts a second earlier, he's obviously going to start in the lead, but look how quickly Eve passes him. Okay, and Eve finishes first. She takes less time.
Evil.
So we're going to see what kind of head start he actually needs. In order to do that, this curve, the shape of Byron's curve is not going to change. Okay, so I'm going to use green next to show his curve at a 2-second head start. So now he's starting 2 seconds before Eve, which means he's going to end, you know, right here. And I can draw my curve. Eve is still going to pass him.
See, this is way too much on such a little graph.
Wait,
It's just a few lines. You can handle it.
Starting higher?
Okay, the next one is going to be in red. Again, he's starting another second early. So all I'm going to do is take his start position back here to -3. I'm going to draw the exact same shape curve as best I can. He's going to end. If he's ending, by the way, here, pay attention. If he's ending after whatever, 8.1 seconds, then this one is at 7.1. Then this one is at 6.1. Does that make sense? If he's starting a second earlier, he's going to end a second earlier. Eve still beats him. And actually, my drawing is just not that good. Eve shouldn't beat him here.
Yeah, in my drawing, you get tied basically with him.
Okay, yeah. That's what it should look like. Pretty much a tie at starting with a 3-second head start. And then my last one I'm going to do in blue. Just pull it back 1 more second to -4. Draw your curve. And there it is. Okay, so this one is Byron at 4 seconds. Red was Byron with a 3-second head start. Green is Byron with a 2-second head start. Purple is Byron with a 1-second head start. And so based on the graphs, what kind of head start does he need?
3-second head start.
to
Yeah.
win or to tie?
To come pretty close.
Basically like 3.
The question says, how much of a head start can Eve give Byron and still win?
2.
3.
I can set her.
Eve can give, let's just say 2.5.
Yeah.
2.5 second head start. And still win. Unless she breaks down. C. Determine the domain and range of each function. Now, real world situation. Okay? Domain. We're going to work this into a little bit of a graph. The equations given are only valid from the time the car starts moving to the time it crosses the finish line, right? So only what's here is valid. We're going to talk about both functions. And actually all the functions are slightly different. So we've got Eve. Okay. We've got Byron 1 second, Byron 2-second head start, Byron 3-second head start, and Byron 4-second head start. The function for Eve with respect to t, cheating a little bit here, but E with respect to t is 10t squared. Byron with a 1 second with respect to t is 5 times t plus 1 squared. Byron with respect to time, Byron with respect to time, Byron with respect to time equals 5t plus 2 squared, 5t plus 3 squared, 5t plus 4 squared. That's all the equations that we're dealing with. And now we want to talk about the domain. And then we're going to talk about the range. This is the function. Okay. So the domain of Eve's function here, can she go less than 0 if t starts when Eve starts?
No.
No. So t, which is time, comes from the set of real numbers, and it must be greater than or equal to 0. It's restricted by negative numbers. It can't be negative. Now, let's talk about Byron with a 1 second head start. His values of t also come from the set of real numbers, but he was moved 1 to the left. He's actually allowed to start 1 second earlier than Eve. So his, for this equation,
-1.
greater than or equal to -1. Okay, what's the next one, the restriction?
Greater than or equal to negative.
Okay, go ahead and copy down the rest. And then thinking about the range. So the range is the set of y values that we're allowed to use, okay? Range. This is, the function is Eve, so when we're talking about range, we're thinking about Eve's distance, which is measured by e, okay? The values that can pop out of this function are e belongs to the set of real numbers, and what's the distance barred by?
Greater than 0.
It's greater than 0.
Less than or equal to 400.
Less than or equal to 400. Okay, so put 0, and then e is going to be greater than or equal to that, and then 400 is the top limit. She's done at 400, right? The race is over, so that's the end. What about Byron? Does it matter if he gets a 1 second head start, 2 second head start, 3 second head start, 4 second head start?
No.
Does it change the range?
No.
What's it going to be?
The same.
B comes from the set of real numbers, and B is in between 0 and 400 inclusive. Notice how when we had a parameter inside the bracket affecting horizontally, t, pulling our graph left or right, it did not affect our range. It affected our domain, but not our range. D.
Oh, there's another.
Yeah, just to think about. The acceleration of each car is represented by the vertical stretch factor in each equation. Does that make sense? Acceleration is represented by the vertical stretch factor in each equation. So compare the accelerations of each car.
The Eve's car is twice as fast.
Accelerates twice as quickly.
Yeah.
Eve's car accelerates twice as quickly. Drag race queen. Way to go, Eve. Your practice problems for
That's you.
this lesson are found on page 129, numbers 1 through 7 and 9.
What was happening
Remember when
here?
you used to